9th or 10th class. So we'll start now. How many of you remember what was taught last time? Because last two classes are converted into doubt clearance session. No?
Yes, sir.
Remember? I'll try to have one more doubt clearance session. I'll be there. Okay. So let us start like this. Do one thing. Okay, let us start. But before that, let me present. Can you see the screen? The
Yes, sir, it's visible.
visible? Good. Why you did not ask any question? Because you understood everything, all of you. We'll see in the exam. I hope you have. Okay, so we'll start with H2 molecule today. Okay, let us start with H2 molecule. So H2 molecule has 2 electrons, no? 2 electrons. Some work is going on, so you may have some noise, but I cannot help. Anyways, so you have 2 electrons, then how does it look like? So you have 2 nuclei, nucleus A, nucleus B, and you have 2 electrons, no? Electron 1, electron 2. So distance between 2 nuclei is called capital R. Distance between nucleus A and electron 1 is called small r, A1. This is small r, B2. What's the distance between these two? It is R12. Obviously, you also have this distance. This is R, A2. And what about this? This is R, B1. So if I write down the Hamiltonian operator in atomic unit, can anyone tell me how it is going to be? I hope you know all these things now. Can anyone tell me what is the Hamiltonian? There are 27 people I can see. So can anyone tell me what is the Hamiltonian in atomic unit? Maybe I'll take names then. So Jaideep Mondal, tell me what is the Hamiltonian? Jaideep, are you there?
Yes, sir. Yes, sir. I'm there.
Yeah, tell me the Hamiltonian. What is the Hamiltonian? Tell me. So people, after I asked this question, I think many people left. Anyways, so what is the Hamiltonian?
So 1/2 del 1 square plus 1
Yeah,
by 2.
so yeah, right, minus. Okay. So the first is this. You have electron 1. So it is like, this is how it is, isn't it? Then
Minus
for
1/2
electron
del
2,
2 square.
electron 2. What else? What else?
So the attraction parts are nucleus to electron.
Okay. So one is this. Then
Electron repulsion and nucleus repulsion.
electron repulsion and nucleus repulsion. So electron nucleus is 1 by R, 1, 2. And nuclear repulsion I can add, but I just you can add it. But anyways, I do like this. This is Hamiltonian. This is Hamiltonian, no? But because of this term, this electron-electron repulsion, this is almost impossible. Not almost, it's impossible to solve analytically, Problem. To solve exactly. So how can you solve? You can solve it numerically, or you can adopt a technique like variation or perturbation. So we'll talk about variation here. So what is the equation I want to solve? This equation is your eigenvalue equation. No? This operates on this, gives you this. Isn't it? Now tell me, what could be the trial wave function? Let us start like this. A good trial or guess wave function. And tell you that for hydrogen molecule, even for H2 plus, which we did, we can start with either this one, which is called molecular orbital trial wave function, depends on the electronic coordinates of two electrons, or there is one more which is called valence bond. Description I'll explain. So this is okay. Is this clear? Is it clear that there are two possibilities? Now, suppose there is no 1 by R12 term. What does it mean? There is no electron repulsion. Okay. So if there is no electron repulsion, these electrons will only fill the presence of nucleus. Okay. So electrons will only fill nuclei. So when electron 1 is close to nucleus A, it is like hydrogen atom, isn't it? And when electron 2 is close to nucleus B, it is like another hydrogen atom. Okay. So in that case, I can start with a trial wave function like this. What will be the trial wave function? In this case, this is, that from your molecular orbital, sigma. So both the electrons are in bonding MO. You remember, these are bonding MO means sigma.
Sigma G1s.
Yes. Sigma G1s. No, yeah. Time to time, please answer. Otherwise, it's very difficult for me to. This is the description. Okay. Remember what is the expression for sigma G1s? R1. It is going to be 1 by, I remember this, root over
2 into 1
1
plus
plus,
s.
yes. And then you have a e to the power of R A1 plus minus R A1. Sorry, B1. What about this? This is again similar. R A2.
B.
This is electron. Very good. Sorry for the handwriting, but you understand what I have written here, isn't it? This is fine. Is this fine? Okay, I
Yes,
missed
sir. Yes, sir.
something, which is root over pi here, I think, a factor. If you check, there's a factor of root over pi for 1s orbital. Because this is nothing but, this is what? This is actually psi 1s 1s orbital for electron 2. Psi 1s A R2. This one. Okay, so you know this. So if you multiply these two, What I'm going to get? What I'm going to get? Are going to get the trial wave function. This is trial MO. Okay. And then what should you calculate then? Then you should calculate the script E. You remember the expression? What is the expression? For script E, it has to be this trial wave function. It is something like you take the trial wave function, take a complex conjugate of that. In this case, this is real. This one. What will be the in between? This is the Hamiltonian. Sorry, this is MO. And then I integrate over the volume element. What is in the denominator? This thing you know now.
Yes, sir.
Should not be a
Normal.
problem. Yes.
And the volume element.
Yes. Very good. Who is this? Who is
Sir,
this?
sir, ion.
Ion. Okay. Now this is quite involved calculation. I am not going to do it. You can try doing this if you want. It is quite involved calculation. But if you calculate this, you'll get script E. And you know, whatever I did for H2 plus, it is possible to get. So let us draw this, the potential energy curve for H2 molecule. Okay, so if you do this MO calculation, MO calculation would give you like this, like this, like this. And if you ask an experimentalist, they have also generated this potential energy surface from experiment, and they have got it like this. This is hand drawn. Okay, this is hand drawn, and so this is not. So this R is 0.74 angstrom, capital R E. This is experiment. And if I ask you what is the value for theoretical calculation, MO calculation, this is above, slightly larger than this. It is, sorry, 0.83 angstrom. Okay, slightly larger. But then I have a problem because this is a dissociation energy. And this dissociation energy, if you do a MO calculation, it is something like 2.65 electron volt. Whereas if you do an experiment, you will find the dissociation energy shown here is something like experimental is 4.7 electron volt. So the dissociation energies, they differ a lot. What you get from MO calculation, molecular orbital calculation, and experiment. Okay. So this is an internuclear distance. One more thing, that this is called the dissociation limit. Correctly. Because if I take hydrogen molecule, if I stretch it, and if I go further, you should get one H atom, another H atom. And by definition, this energy is zero. So at a large internuclear separation, your energy should become zero. Is this clear? So it should be something like this shown here, as you get from experiment. But if you do a molecular orbital calculation, you don't get the dissociation limit correct. Because it gives you energy which is higher than zero. That's a problem. And also the dissociation energy, they differ by 55%. Huge difference. So it is not a good description. Okay. So MO does not give you the dissociation limit correct. That is one thing. It also does not give you the dissociation energy correct. Also, the bond length obtained from MO is slightly larger than the bond length, equilibrium bond length one gets from experiment. Is this clear? Now let us consider another case situation where you have, this is your one is A on nucleus A, and this is one is B. Okay, and they are separated by large distance. When they are large, they are separated by large distance. So what would be the trial wave function in that case? If I see this picture, this is your trial R1, R2. I am just changing the notation. I'm making my life easier. I'm calling it 1, 2. If I call it 1, 2, it is fine with you? Because I don't want to write R1 bar, R2 bar
Yes,
again
sir.
and again. This is for 2 electrons. So this is a situation when these 2 electron, those two nuclei are largely separated. So, so electron 1 is close to nucleus A, electron 2 is close to nucleus B. And in this case, an approximation would be given by the product. This is the approximation. Okay.
So here the second electron does not feel the attraction of the
Yeah,
first
yeah,
nuclear.
yeah. So it is the attraction, and this is true when they are separated by large distance. But we assume, for the time being, also assume it is a trial function even when r is small, which is not a good description, of course. But assume that when r is small, then also it is a trial wave function, and you can do an calculation. If you do a calculation with this, let me write, this is the experimental one. And if you do a calculation with this, you will see that it gives you something like this. And this gap is now 0.4 electron volts, extremely small. So what you see, that dissociation energy is totally wrong. Prediction is nowhere close to experiment. Experiment value is like 4.72 electron volts, and you get 0.4 electron volts, not even 10%. But what you must have seen here, by construction, it predicts the dissociation limit correct. It correctly predicts the dissociation limit. Can you see that? Why? Because you start from the dissociation limit. You start from a large distance where these two energies are the energies of two hydrogen atoms, and that is by definition I see that is my zero of energy. So that's why the dissociation limit is correctly predicted, but it gives you a very bad dissociation energy, which is this. So basically this tells you it's not a very good wave function. How can you make it slightly better? Any suggestion? How can you make it better?
Linear combination of the two assumptions we taken.
So the point is, when the distance between the nuclei is small, so what happens in that case, the electron 2 may be found or associated with nucleus A, isn't it? Electron 2 could be close to nucleus A, associated with nucleus A. And electron 1 could be found close to nucleus B or associated with nucleus B. What does it mean? It basically means that you cannot only take this. You cannot take only this. You should also, one should also consider, can anyone tell me what is that? If electron 2 is associated with nucleus A, then I should have here
1s2.
1s2, yes.
yes.
1s1.
So this. So you cannot take only. So this one. And you know what to do. What you should do then? A good
Linear
like
combination of these two.
good thing would be something to take a linear combination, just like C1 times this psi1 is A1, psi1 is B2 plus something like 1s2 psi 1. Okay, so take a linear combination. But look at it, this is different from your MO picture, isn't it? Okay, and actually one can calculate. If you want, you can calculate. First of all, it is obvious that C1 has to be equal to C2 from this combination, isn't it? Because I cannot give preference to this or this. Both are equally probable. So C1 has to be equal to C2. And one can show that C1 is equal to C2. And in this case, this is slightly different. It is given by, I don't know how many of you know this. It's 2 into 1 plus S square. Has anybody done this calculation before? You have 1 plus S square. This can be shown. Has anybody done this calculation?
No, sir.
Anish, have you done it?
I can't remember.
Yeah. This is for the ground state. And this description is called, this description is called valence bond description or valence bond theory, VBT. So ground state is, according to valence bond, is VBT. What notation? I don't know. Yeah, for the ground state. Also, you have for the excited state. Can anyone tell me what will be the answer? Actually, you'll see that this is, it comes with a minus sign, and here also you have a minus sign.
Minus.
But this is different from your MO. Look at it. This is from your MO description, isn't it? And then one can calculate script E. And once you do this calculation, you can actually plot your electronic energy the way I showed for the MO calculation. So I have to, so your MO calculation was something like this, not predicting the dissociation limit correctly. Your VVT calculation, if you do, you will see, this is your MO, This is VVT. An experimental one is maybe below this. These are hand drawn, so don't worry. Okay. And also it predicts excited state like MO. And this is repulsive, no? There is no bond formation. No bond formation. So I'll give you a table RE versus and DE. Okay, if you do a MO calculation, then RE is gave you I think 0.83 angstrom. DE was 2.65 electron volts. Okay, if you do the simple VVT calculation, the one I showed you, you get it is 0.80 angstrom and DE is 3.16 electron volts. And if you do experiment if you do, you get 0.74 angstrom. This is 4.72 electron volts. And actually you can do an improved VVT calculation. Improved VVT calculation, if you do, it gives you 0.77 angstrom and gives you 4 electron volts. Now, what is this improved? This is probably due to these people, James and I think this college, and also this is predicted by another person called Wenbaum. I think maybe he did this. I have to check this. So, what do you mean by improve VVT? You don't forget that you are doing a variational calculation. Improve VVT means you have more variational parameters. What could be the variational parameters? Any guess in this case? This coefficient C1, C2, of course, you can. Other than that, in the orbital itself?
Nuclear charge.
Yes. So you can do this nuclear charge could be your variational parameter. Okay. Now let us go back to MO and see what happens to MO. Why MO gives totally wrong dissociation limit. Any idea why it gives?
It also considers the case where both electrons are in the same nucleus. In the dissociated limit.
Okay. So my question is why MO gives totally wrong dissociation limit? Okay, that's the question. So let us
Sir,
see
because
phi
it,
MO. Yeah. Tell me.
sir, because according to it, it assumed to be totally covalent. I think, sir, this may be the reason.
Yes. Totally covalent. Or the other way. So let us see. So these are the atomic orbitals. If I do this, I'll get molecular orbital. I'll get something like here. Remember the prefactor. What is the prefactor? I think that is the one. No, 2 into 1 plus s. What is the prefactor? I think that is the
Yes.
one.
Yes.
Square of it because you are taking a product, and then you have psi 1s a. Sorry, this is one. Huh? Because this is for electron 1, this is for electron 2, 1 and 2. So this will give me, if I expand this term, what I'm going to get, first term is psi 1 SA 1, psi 1 SA 2 plus psi 1 is B 1, psi 1 is B 2 plus psi 1 is a 1.
So I think there should be a 1 over pi term should be there.
No pi term. Because I'm writing only one essay. Why would it be? If I'm not writing the expression itself,
Okay, sir. Okay.
there will be no such term. I think this is how it is. Anish, did I do any mistake while writing? There are 1, 2, A, B, all these things are there. So look at this term, these two terms. Have you seen it before? Have you seen it before, these two
That is
terms?
the VBT terms.
Yeah. These are like VBT terms, isn't it?
Yes, sir.
Now here, VBT terms assume that one is A1, one is B2, which basically means nucleus A has electron 1, nucleus B has electron 2, or the other way. But what about these terms? What does it tell you? What does it tell you? It tells you, the first term tells you that nucleus A has both the electrons, and the second term tells you that the nucleus B has both the electrons, isn't it? Okay?
Yes, sir.
So this one actually tells you, this is predicting a dissociation limit like two neutral H atom, isn't it? These two terms. What you get from VBT, as well as it is also included in MO. But in addition to that, in MO, you have two other terms. What is this term? If I write the same way, here both the electrons are on nucleus A. So this is like H minus H plus. What about this guy? This is
H plus H minus term.
H plus H minus. So these are called ionic terms, no? And these are covalent.
Covalent.
Okay. Now this experiment is H2 dissociates into H plus H. This experiment I'm talking about. It is dissociating into two neutral H atom. So if you do MO calculation, it also has ionic terms in it. So as a result of that, it will predict this experiment, the one I've shown here, it will predict that dissociation limit wrong. Is this clear? These are ionic structures, ionic terms. So these are ionic structures. Is this clear to all of you? Because you have these two extra things in your MO description. And you want to predict a dissociation limit where the H2 molecule dissociates into two neutral H atom. Your MO would not predict that limit correctly, but VBT would, because that is how VBT is built. Okay. And one more thing, if I want to include spin, what should I do? How do I incorporate spin here?
We multiply with an antisymmetric spin component.
See, the wave function is symmetric, no? The total wave function has to be antisymmetric, no? So actually, what you should do, you should take this wave function, phi m, or whatever you have it, 1, 2, and you multiply it with this alpha 1, beta 2, minus beta 1, alpha 2. This is antisymmetric. The whole wave function is going to be then antisymmetric, and it will follow Pauli's principle. Is this clear? And this is the same thing will happen with VVT. You can do it with VVT. It will happen same. In case of VVT also, you do the same thing. Go and check yourself. Now I come back to this covalent and this thing. So covalent means I have two electrons, both are equally shared. This is what covalent is, isn't it? The Lewis structure, you know. And then ionic structures, I told you that you have a situation like H minus H plus or H plus H minus. Okay. Now how to improve, but one can design an experiment where H2 will dissociate into H plus and H minus. Then that dissociation limit will not be predicted by your VVT, the VVT so far I've talked about, isn't it? Is this clear?
Yes.
That dissociation limit will not be predicted by VVT. Then how to fix your VVT so that this limit is predicted? Any suggestion? That okay, I have, depending on the experiment, I can have H plus H, I can also have H plus and H minus. So I should have a more general VVT trial wave function. And what should be that more general or improved VVT wave function? Any idea? Any
Sir,
suggestion?
if we add covalent terms in that,
Yeah, you know that from your MO, in that case, this improved valence bond description would be something like, this is 1, 2. You take something like, say, pi, where you have this H double dot H, which is a covalent, plus phi H minus H plus phi H plus H minus. Obviously, these two terms will contribute equally because H plus H minus and H minus plus H plus, they are actually identical. So both of them you can put together, put a coefficient here, C1, put a coefficient C2. The C1, C2 are variational parameters. You can vary this, and that is why those people have come up with better numbers, better equilibrium bond length, and better dissociation energy. Is this clear? So this is how it can be improved. This is the improved valence bond description. We will not discuss valence bond further because all the valence bond works very nicely with hydrogen molecule. It is better than the MO, the simplest MO description. But if you go to a system where you have more than 2 electrons, many electrons, like many means like 3, 4, 5, whatever, then this valence bond description doesn't really work. And people have seen that it is better to do molecular orbital calculation. So in all the chemistry, quantum chemistry groups, not all, in many groups, people do this kind of MO calculation, and they make use of packages like Gaussian and other packages. Essentially they do a function based calculation, means most of the time they do molecular orbital calculation, to predict chemical reactions, bonding, all these things. So it is good to have not good. It is, you must have a good understanding of your MO theory if you are a chemist. So we'll now go back to MO theory, and now we'll discuss MO theory. So let us go back to H2
Sir,
molecule, which
so we can also
started.
improve, sir, MO.
Yeah, we can also improve MO. That
So, but
depends
only
on,
you are, sir.
yeah. You can improve MO. What happens then in MO, you have these integrals, no? Those integrals you can evaluate better using better techniques. That is how you can improve MO. I will talk about how to improve MO. It's a linear combination of atomic
Okay.
orbitals. No, you can add more atomic orbitals and construct MOs which will predict bonding better. All these things, which we'll briefly discuss now. So what we had was like that. We had two molecules HAA, not two molecules, two atoms HBB, and they form this one and this one. This is your sigma G1s. It is sigma U star 1s. You remember this, no? If it is H2 plus, you have one electron. Then you put the electron here. If you have H2 molecule, you have two electrons. Then you put another electron here. They're paired. Okay. So now H2 plus, if you go back and check your notes, it has a bond length of 1.06 angstrom, and dissociation energy was 255 kilojoule per mole. For H2 molecule, this is 0.74 angstrom, and this is 431 kilojoule per mole. Of course, you know, for H2, there are two electrons that are equally shared in the covalent description. And then, you know, there is how many bonds are there in H2 molecule? One bond, isn't it? So if I follow this definition, so roughly, it will also have the H2 plus would have what? Half a bond, isn't it? So in order to describe this, one can define what is known as bond order. I think everybody knows, no, what the bond order is.
Yes, sir.
The bond order is given by like this: the number of electrons in bonding MO minus number of electrons in anti-bonding MO. But that will not be enough. You have to divide this by 2, multiplied with half. That's the definition of bond order, isn't it? Because if I follow this definition, for H2, what is the bond order? Is half into 2 minus 0, which is 1. For H2 plus, what is the bond order? So that's why you see that for H2 plus, the bond distance is larger, equilibrium bond distance, compared to H2. Okay. Now, what about helium-2? If I have a molecule like helium-2, what will be the bond order? Helium-2 bond order is going to be
0.
why? Because of this, no?
Yes,
Those
sir.
2 electrons are also in anti-bonding. If you see carefully, it is not shown here, but actually it is not. This gap is larger than this gap, smaller. This is larger, this is smaller. So if you put 2 electrons in anti-bonding, definitely this molecule is not going to be formed because this will be very, very unstable. So putting electrons in anti-bonding makes the molecule unstable. It causes instability. Is this clear? And if you go and see the expression of this bonding, the gap between HA and antibonding orbital is larger than the energy difference between bonding and the atomic orbital energy. You can go and check. But now let me recall what we had there in your molecular orbital picture. We had a matrix. Do you remember the matrix? HAA minus script E, HAB minus
Script E into S.
S. Here we had HAB, of course, to script E into S. What we had here?
HBB minus script T.
And then we had this. Please remember this expression, this thing. It is very useful. So if I expand this, you know that I have to solve the determinant, which is equal to 0. This leads to this quadratic equation. Suppose you have a situation. What is the situation? Situation is such that your HAB is 0, S is 0. S is what? This is called overlap integral. And HAB has a name. How many of you know the name? This is called resonance integral. We'll talk about it little later, maybe today itself. And if both are 0, what is going to happen? This your script E would have two possibilities, no? These are the two roots, which basically means what? If script E is HAA or HBB, what does it mean? Can anyone tell me what does it mean?
The single atom.
It basically means no mixing, isn't
Yes,
it?
sir. Yes, sir.
Chaos. No bond formation. So in order to have bond formation, your overlap integral and the resonance integral has to be, they have to be non-zero. Is this clear? From this thing you can see, from this simple analysis, you can see that. Is it clear? It has to be. Otherwise, there will be no bond formation, no splitting. Now, if I give you a case like this, that okay, now HAA is not equal to HBB, and you have a situation that this is where HAA is, and this is where HBB is. This will happen when? Can anyone tell me? HAA, HBB, they are not same. When this is going to happen?
Heteronuclear diatomic.
Yes, sir.
Yeah.
Heteronuclear.
So this will happen when you have a heteronuclear diatomic, no? If you have heteronuclear diatomic, this is going to happen, isn't it? So in this case, what will happen to the bonding? You will see that the bonding MO would be close to HA, and anti-bonding MO would be this is bonding, this is anti-bonding. So bonding MO would be close to HA, and this anti-bonding MO will be close to HBB. This is another thing you should remember. So bonding MO is closer to HA and anti-bonding is closer to HBB. Is this clear? This is how it is. So let us now try to do a molecule like lithium-2. Lithium-2. So let us start from here. This is not heteronuclear diatomic, this is homonuclear diatomic. So this is your 1s, this is your 1s. Then you'll have 2s, 2s. Okay, now 2p, where it would be? Where it would be? 2p, will it have same energy as 2s or different? Whether it will have same energy as 2s or different? Tell me. Very simple question, whether 2p would have the same energy as 2s or different.
So different.
Why different?
So for a light too, na?
Yes. Why different? Tell me.
So for
Your
single
answer is
electron
correct.
we can, sir, for single electron only 2s equals to 2p. And sir, but
Yeah.
it is multi-electron. We cannot say 2s equals to
So
2p.
yeah, so what happens? Single electron, you have one electron. There's no electron repulsion. In that case, energy depends only on the principal quantum number, hydrogen molecule. You have done it, isn't it? Not hydrogen molecule, hydrogen atom. You have done it. So, but if you go to many electron system, what happens? This electron repulsion will come into play, isn't it? And as a result, these orbitals will now, the orbital energy will not only depend on n but also on L. And if you do a calculation, you'll see that 2s and 2p would have different energy, and 2p will have a slightly higher energy. So I should draw something like this. This is because of electron repulsion. So I should have 2p here. There are 3 2p orbitals, no? So I can write like this. So 2s and 2p have different energies as this is a multi-electronic system. Electron repulsion. Okay, up to this is fine. Now experimentally, this R equilibrium for lithium 2 is 2.67 angstrom. I think that's the value. Yes. So as a result, I can say that s orbital are quite inside, no? For atom, you have 1s, then 2s, then 2p, like this, isn't it?
Yes,
One
sir.
is quite interior. So if the bond length is quite large, 2.67 angstrom, this 1s orbitals do not, so 1s orbital from one lithium and the 1s orbital from the other lithium, they do not interact much. Okay. So as a result, I can say they are kind of inert. Okay. These orbitals, in this case, lithium. Is this fine? Is this argument fine with all of you?
Yes, sir.
Yes, sir.
Buried. Right, sir.
Yeah, buried, whatever you want to call it. So we'll
Yes,
not
sir.
bothered about 1s. What about 2s? Of course, 2s will interact and they'll form, what is that going to be? I'm not going to draw the orbitals. You can draw yourself. So this will give you something like, what is that called? Sigma orbital. What type? G.
Yes, sir. Sigma G2s.
And this will give you something like sigma U.
U2s star.
This fine? This okay, no?
Yes, sir.
There's a hand drawn. Okay. Now your electronic configuration is 1s2, 2s1. You have one electron in 2s. Now this 2s can interact, so it can mix, obviously. What about 2s on one lithium and 2p on other lithium? Will they interact or not? Will they mix or not? What do you think? So let us go to the other slide. Yeah,
Their
understand
energies are
the
different,
question I
so
asked. Their energies are different, but not much different. No? They're slightly different.
They can
Okay,
interact.
so they can interact. So
Right.
maybe if I assume that the internuclear distance is along Z, then what will happen? 2s and 2p. Which 2p? Any suggestion? Which 2p will interact?
2p0.
Don't say
2pz.
2p0.
Yes, sir.
You have XYZ. You are a chemist.
2pz.
No 0, 1, 2. Huh? 1 minus 1. Anish, you have 2px, 2py, 2pz.
Yeah, 2pz.
2pz, yes. Yeah, 2p0 is fine, I understand, but better to call 2pz. So why 2pz? So let us try 2px first. So how many of you remember how 2px looks like? Is this fine? This is your 2px, no? Because z is this internuclear distance. So this is x and this is y towards you or away from you is y. Okay? This is z. This is x. This is y. These are three axes. These are three axes. Okay? Now tell me how does a 2s look like and why it will not mix with 2p x. Anish, any suggestion? Why?
The overlap integral will come out to be 0.
Yes. So how do you calculate the overlap integral? Now 2s, you remember? How does 2s look like, Anish?
Spherically symmetric.
Yeah, but one more thing is there, no? 2s has a node.
No node.
Yes,
Yes, one node.
it
Yes.
does have a
What node it has?
radial one.
Yeah. So actually, if you look carefully, you'll see 2s as this, isn't it? This is 2s.
Yes, yes.
In some books, people will actually argue that this is 2s. And they will draw, sorry, like this. But this is actually 1s, isn't it?
Yes, sir.
The same argument will hold actually. So let us see the 1s and 2px interaction. What will happen to the overlap integral? This plus and this plus will give me what? Something like plus. But this plus and this minus will give me something like minus. And then you have to sum this.
Initially they're same and will give
It will be 0. Same amount of plus and same amount of minus. If you add them, it will be 0. Is this clear? Because what is an overlap integral? Overlap integral is something like, in this case, psi 1s star. I don't want to write. Okay, if you want, you can write. This is like sum. Integration is summation, isn't it? So you see the overlaps, you find the overlap and then sum the overlaps. So one overlap would be like plus plus and then plus minus, but they'll be equally overlapped, but with different sign. When you sum them, this overlap integral is going to be 0. So 1s and 2px will not mix because the overlap integral is 0. Is it clear to all of you? One s and 2px. What about 2s and 2px? Will the same argument hold here?
Yes, sir. Same argument hold here.
It is little complicated, but the same argument will hold because you see the outer portion is minus. This minus and plus will give you minus. This minus and minus will give you plus, but equal amount. So they'll cancel. And again, this plus and plus will give you small plus. Then plus and minus will give you small minus, and they will be also of equal amount. So they will cancel. So something like you have minus, then you have a plus, and then you have a small plus, and then you have a small minus, and if you add them, it's going to be 0. So in this case, the overlap integral is, so Anish, you have to be careful, no, while dealing with 2ps.
Yes,
So not
yes.
2ps, 2s. Huh? Usually it comes to your mind, it is 1s, no, all the time. I think
Yes, yes, yes,
many people make this mistake. Make this mistake. So you should not be making this mistake. Okay?
So maximum it may be one, na?
Oh, yeah, of course. It will be 1, but it doesn't matter. What I'm saying that it is 0 in this case. What
Okay.
about 2s and 2pz? Again, 2s and 2pz, if you ask, most of the people will draw 1s and 2pz. So 2s and 2pz. So let us do 1s and 2pz first. This is 1s, 2pz, you remember? This plus is on your right. This is my convention. What will the overlap integral in this case? What will the overlap integral?
Non-zero.
It is 0 or 1 or like, sorry, 0 or non-zero? That's the question.
Non-zero.
Non-zero. What will be the value? It could be minus, could be plus, depending on the orientation, isn't it?
Yeah, here it
Whether I
is.
draw it like this, in this case, it's negative, I think. But what is important is 0, not 0. Is this clear? Because this plus and minus will overlap, give you something like minus, isn't it? And this plus and this plus will overlap, give you some plus, but that overlap is smaller compared to the overlap between this plus and minus lobe. This minus lobe and the plus of your 1s. This is equal to non-zero. This is fine. Anyway, I'm not going to do it. What I'm interested in here is this 2s and, sorry for the very bad drawing, but 2s and 2px. What is the value of s? Is it 0 or non-zero?
Is non-zero.
Yeah, because again, you see that this minus and minus will give you something like plus. You multiply. So it is not only non-zero, it is mostly positive in this configuration. If you take 2px on the other side, it will change sign, but it is non-zero. Actually, s is greater than 0 in this case. So they will mix. Is this clear to all of you that they will form molecular orbital? Is it clear to all of you that they will form molecular orbital? Should be clear to all of you.
Yes, sir.
Okay, now you also have 2s. What about 2s and 2py? Same argument will hold
Yes, same as the 2px.
because it's in 3D, no?
Yes, sir.
It should be same. Okay, so I'm not repeating that. What about 2p from one lithium and 2p from other lithium? Will they mix?
Yes, sir. They will make.
They will mix, no? So what kind of mixing that they can have? So they can have a situation. So let us draw like this. Sorry for this bad, huh? This one. If I have this kind of combination, what will happen? This will give me what? Is it bonding or anti-bonding?
Is bonding.
Head-on collision. This is 2px, not 2px.
2pz should be.
Yeah, it should be. I have been telling this. And this is 2pz. This is 2pz. Okay, 2pz, 2pz. So what will happen to this if they combine? What will happen?
One bonding orbital will be formed.
Yeah, so it will have something like, you remember this, no? This is bonding. How many nodes it has? Okay, another, let me check the another combination. Another combination is this. Another combination.
This is
So what will
anti-bonding
happen
one.
is this is anti-bonding, no? Anti-bonding would be something like, can anyone tell me how does it look like? It will look
Electron
something
density
like,
between two nucleus will be less. Yes,
this
sir.
is plus, this is minus, and then have like this. This is minus, this is plus. Now, in bonding, how many nodes are there? Tell me.
Two nodes. No,
Yeah, because because you already had these two nodes, no, one this. So you have two nodal surfaces.
yes, sir.
What about anti-bonding? You have these two nodal surfaces, no? What else?
Another one is there.
You also have this nodal plane.
Yes,
So
sir.
how many nodes are there?
3 nodes.
So it has higher number of nodes, so higher in energy, isn't it? Okay, is this clear? So if you put an electron in the bonding MO, it will build up the density between the nuclei. But in antibonding, no such thing happens. Okay. Now, what about the type of orbital I have drawn here? What are these orbital? These are sigma or pi? I'm not talking about pi, but you know, what are these
The
orbitals?
sigma symmetry.
How do you know it is sigma symmetry? How do you know it is a sigma symmetry? You're right, but how do you know? What is sigma symmetry? What is sigma symmetry?
So be cylindrically symmetric.
Yeah, because see, sigma and pi, sigma comes from cylindrical symmetry. What is that? So if you draw an axis like this, and if you rotate this orbital,
It
MO,
should be
point
indistinguishable.
orbital, yeah, it doesn't change.
Yes, sir.
So that's why it is sigma. Here also it is sigma. You have a cylindrical symmetry. So this is a sigma type orbital, of course. It is formed between by combining two 2p orbital, 2pz. So sigma g, 2p or 2pz. This is fine. If I write like this, what about this? This is going to be sigma.
So U
Why it is
star.
g? Why it is g? That you remember, no? Because you have, if you take one point from here, and draw a line passing through the center of the molecule, center of inversion, then that point should not change sign. Then it is Gerard. Then it is G. Now it changes sign. Then it is
U.
ungerad.
Yes.
That is U. So in this case, this will be G. This will be U. Of course, 2pz. But again, I have to put a star because it is the anti-bonding. Is this clear to all of you? Is this clear to all of you? Now, what about this combination? Two px on one lithium, 2px on the other lithium. What about this combination? What will happen?
Sidewise overlap.
Sidewise overlap, okay. But in this case, you will see this overlap is not as efficient as head-on, but still it will overlap and it will form a MO like this. And you have one nodal plane, no? But you can also have a combination like this. This will give me what? It will give me
Antibonding.
here. How many nodes are there? We had this node as well as you have two. This
Two
one,
nodes,
no?
right? Yes, sir.
Two nodes, two nodal planes actually. This is anti-bonding. Now, what kind of orbitals These are what kind of orbitals? These are what kind of orbitals?
These are called pi orbitals.
Pi orbital. But why it is called pi? Anybody knows why it is called pi? Because it doesn't have that cylindrical symmetry. Why? Because if I huh?
They are
Go
cylindrically
ahead.
antisymmetric.
Yes, because if I rotate like this, plus will become minus, minus will become plus. It will pick one minus sign, isn't it? So that's why the same is here. So that's why they're called pi. This is pi. Okay, this is formed between 2px. So I can write pi 2px, but it is sigma or g. Tell me. If I take a point here and go through the inversion, what will happen to the point? It will change sign.
It's pi
So the
u.
bonding, this is bonding actually,
Yes, bonding is pi u.
but this is pi u, isn't it? What about this guy? This is pi
Pi
g
g star. Yes.
to px, isn't it? Because here plus will become plus, minus will become minus if you go through the inversion, the point of inversion. Okay, is it clear to all of you? Cylindrical symmetry gives you sigma. If you don't have it, then it's pi. And then inversion operation, if the operation changes sign, it is u. If it does not change sign, it is g. And star is if it is anti-bonding. Very simple rules. Very simple rules. Okay, very simple rules. Now with that, let us try to construct MO for a general diatomic molecule. So I'm not considering 1s, I'm just considering 2s. Okay, you have 2p here, 2p here. This will give you this and this. What is this? This is sigma g 2s. This is sigma u 2s star. Fine. And 2s to p gap is there, but not much gap. So what will happen? First of all, I have already shown you what are the possibilities. One is sigma orbital between what and what? 2s and 2pz. This will give you something like this. This and this. What is this called? Tell
Sigma
me.
2pz.
Something you can call it. And then what about, you have 2 pi orbital, no? Px and
Yes.
py. So this one I call it sigma g 2p. It could be px or py. And also you can have head-on collision between 2p. So 2s and 2p and 2s will consider later, but 2p and 2p will head-on collision and will give you sigma g 2p I have done. Yes. This is what it is. Sorry, this is pi. This is pi u
Pi u
2
2p.
2px or 2py. Yeah. This one, and this is sigma g. Sorry for this. Okay, we're almost done. Just wait for a minute. Almost done. What will happen to the anti-bonding? You'll also have similar anti-bondings, no? The one I have just drawn. Some problem with I just need 2 more minutes and then I'm done for today. Okay. And what about this? I will have then this. What is this called? This is called pi g star to px or to py, and this is sigma u star to pz. Is this clear to all of you? This is how it is. Is it true for all the diatomics, homonuclear diatomics? Is it true for all homonuclear diatomics? Tell me.
We may or may not have sp mixing.
Now, this is true when 2s 2p separation is large.
Large, yeah.
And this is for when the number of electrons is large. Like oxygen, fluorine, like this. But if you go to boron, carbon, 2s 2p gap is small. And then what will happen in that case? I've already discussed that. So 2s and 2p will mix and they'll interact. We will start from here in the next class. What happens when you go to a system where the 2s 2p separation is small, like small number of electrons, like boron, carbon, and this hemodiagram will not hold there. You know what is going to happen? Anybody knows?
The sigma star
The
2s
sigma
and
will shift
Yeah,
upward.
actually, what is going
yes,
to
yes,
happen?
yes,
This goes down, this goes down, and also this goes up.
yes, sir.
If you go and check, this goes down, goes up because of this 2s 2p mixing. And you need that kind of MO diagram in order to explain some magnetic properties of boron. You remember that? Or some other molecules also. So we'll start from here. In the next class, we'll start from here. Okay? So we'll stop here
Okay, sir.
today. We'll stop here today and stop presenting.